Hi guys, welcome to this video. So in this video, we will cover system design foundational concepts in 1 hour, almost 1 hour. So I have divided this video into 5 topics. So the first topic we will be discussing about common terms used in system design, because if you're starting your journey, right, if you're in college, if you're in fresher, or if you're preparing for interview, sometimes you don't remember the exact definition of each of the terms, or you don't know the basic concepts like what is availability, what is consistency, what is eventual consistency, what is latency, right? So all that terms I have put, so it will be 20 plus terms. So I have tried to explain in an animated way so that beginners can also relate to the concepts. So once you know these common terms or common concepts, then the next video or the next section of this video will tell you how to use that concepts to do the scaling. So here we will discuss vertical scaling, horizontal scaling, right? So big enterprise application, whatever they use to scale their application, so we will try to understand that from a very high level perspective. And after that we will discuss quickly on API patterns, like REST is there, GraphQL is there, RPC is there. So we will discuss that high level concepts of API patterns, and then we will discuss about deployment strategies, because this is very important for the big enterprise applications, because when they deploy they don't want any downtime. So you should be aware about different deployment strategies, you should be aware about how to achieve that, and the most commonly used is blue green deployment strategy, which we will discuss in this section. And the last section will be trunk based development model in big companies, so that you will able to understand that if any company have lot of engineers working in a one project, then how they are managing the development life cycle, how they are managing their GitHub strategy, or basically entire delivery cycle, right? So which will help you to understand like how big enterprises are delivering their softwares. Even they have thousands of engineers, still everyone is working in a very structured way. So there are 5 sections. So if you are preparing for interview and you are using this video for revision, this is very good. Watch till end. If you're in college just starting your journey, this video will make your basics clear. Or if you're fresher, or if you've never really deal with system design concepts. Hi guys, welcome to this video. So in this video, I want to discuss high level terms which are often used in a system design umbrella, right? So whenever you are talking about system design, you will be talking about some terms like scalability, throughput, latency. So this is the video which I want to cover first, because if you are complete beginner, so you should be aware about basics of each term. So let's start with scalability and throughput. So in a simple language, if I will cover here, so let's say you have created one program, right? Or program or algorithm. So which is doing something. So your algorithm is doing basic calculations like a calculator. So now let's say you have created this algorithm. Now you want people to use your program because it will help them. So now you have hosted this algorithm in some server. So let's say you have this server here. So I will just search for a server. So let's say you did the coding. So it doesn't matter what programming language you have done, right? You have just created a program. So we will not go through the programming language. So you have some program which do calculation. Now you want other people to use your program because it will help them. So now you compiled your program, right? And then you put that program in the server. Server is like a laptop you have, right? Like you will have a CPU, some RAM, some memory, right? So let's say this server, you put it on a 8 GB RAM this server have. Just an example, right? So now let's say you hosted this. Now I will just search user. So now what will happen is user will call your program which is hosted here, and here the program will run and it will give the response back to user. So this is the request, this is the response. So now this is very fundamental. So you are giving people to use your program, so they are requesting. In request they might send you the numbers, the like what operator they want, and in the response you are sending the result. So for example, in the request you are getting 2 plus 2, and in the response you are sending them 4, and this calculation is done by your algorithm. So now what will happen, this user is very happy the way the program is working, and you are also very happy, and server is able to take the load because there are less users. Now throughput, right? So if I go to this slide, so throughput means number of requests a system can handle per second. So now based on this server, based on the CPU specification, you can say like my application, right, will serve up to 500 requests per second. Most of the times it's being used as TPS, transactions per second, TPS, right, or request per second. So let's say based on your server size, your throughput is 500 TPS, right? So that means this system is able to handle 500 requests per second, is known as throughput. So now the second concept is linked with throughput, like let's say scalability. So scalability means, for example, now your user have grown from 100 to let's say 1000. So you get lot of users, right? So a lot of users are using your application. So now your users have increased, and now we know that this server will only able to handle 500 TPS, but now our audience size is 1000, right? So now we need to do scalability so that we are able to handle the load. So scalability means either what you will do, okay, I will double the size of the CPU, like I will increase my internal so I will increase the RAM, I will increase, put one more core, right? So I will just increase, I will not buy the new server, but I will upgrade my existing server, right? So let's say I will double everything. So now when I double everything, so now the TPS will be 1000 TPS because we have doubled everything, and we have not added new server, but we have done scalability by upgrading the existing server. Now our server is bigger, and now this concept is known as vertical scaling. So vertical scaling means we are not adding the server, we are just upgrading the existing server. So now let's say your consumers are now again double. So now it is like 2000 users wants to hit your application every second. But now your application is only able to support 1000 TPS. And now there is a limit, right? You can't keep on increasing the single machine because there is some limit you will able to add the infrastructure to the single server. So now the second type of scaling is horizontal. So now what you will say is I will put one more server here of same size. So I will just delete this, right? And then this is also 1000 TPS and this is also 1000 CPS. And now we have put one more server like this, right? So this concept is called as horizontal scaling. So I will put more servers, right? And I will call it as a horizontal scaling because now we are not increasing the specifications of the existing server, but we are increasing the number of servers. So now this concept is called as scaling. So we have covered scalability, we have covered throughput. Now we can go to latency. So latency is time taken to process a request and send back a response. So it's simple, right? Like let's say your user is calling your program and then user is getting response. So user should be aware how long it will take. Just simple. Like when you order anything from restaurant, you always ask like how long it will take. So they will say 15 to 20 minutes. So that means that 15 to 20 minutes is a latency to prepare your order and give you your order in a ready state. So same thing is with the program, right? So here you can say, okay, latency of simple calculation can be like, let's say 5 milliseconds, but if the calculation is like complex, it can increase up to 10 millisecond, right? So in engineering or system design terms, we can call it as latency can be 5 to 10 millisecond depending on request. So in that way we can design our system, or we can convey to our consumers what's the latency of our program or algorithm. Now our next term is load balancing. So load balancing means distributes incoming traffic across multiple servers, avoiding single server overload, right? So basically what will happen here? So let's say when we added two servers, I will remove this vertical scaling keyword. So now we have two servers, right? And now if let's say this user is calling your program, now how you will decide it will go to server 1 or server 2, right? So let's say this is S1, right, or server 1, and this is server 2. So now you need something right in between to decide where the request should go. So in that case, load balancing comes into picture. So what will happen is, so I will put here load balancing layer, right? So it will be load balancer. So now every request, right? So if I will just copy this and put it here, right? So now every request, so let's say these are all your users. So these are your users. Now every request will go to load balancing first, right? And load balancer will decide like where the request should go. So either it can go to server 1, either it can go to server 2, right? So this is how the load balancing works, and there are different algorithms. Like one way is round robin, like first request will go to server 1, second request will go to server 2, third request again will go to server 1, fourth request will again go to server 4. So it's a simple round robin algorithm, but there are other load balancing algorithms based on different use cases that anyways we will discuss further in the course. But high level, you should be aware about load balancer concept, that why it is needed. Then we will proceed with caching. So caching means temporary stores frequently access data for faster access, reducing the DB hits. So most of the times we will save the songs offline, like from the YouTube or Spotify, we can download, and then even we don't have internet, we will able to play, right? So it's kind of a caching or storing we are doing within our local memory. So same thing will happen here. So clean this a little bit. So let's say we have server here, right? And then we have a user here. So what will happen is, so I will not put load balancer here, but eventually it will something look like this. Let's put a load balancer also. So I will just do like this, load balancer here. And then what we will do, the user will hit the load balancer, and then the load balancer will decide where the request should go, right? So where the request should go, either server 1 or server 2. So something like it should be look like this. And then I will also search for database, because most of the application will fetch the data or insert the data from database, right? So let's say this is coordinating with database, and then from the database the result is coming, and then your program is processing that result and sending back to a user, something like this. So again, this is very basic, we will cover in detail in the further videos, but overall the request flow will look like this. So request will go to load balancer, then it will go to any server, and from that server it will call database, and then your program will do the logic, business logic, and the response will be sent back to user. So this is a high level flow, or you can say flow for most of the applications. Now what will happen is, let's say you are getting similar kind of request, right, every second. So just imagine every second you are getting to get all products, or let's say get any particular product, and every time what you are doing is you are going to the database and then you are fetching the result. So what we can do is, like, we can have something stored inside the server. So we can use like caching. So what caching will do is, caching is like a in memory, we can use Redis, or there are different caching providers, but we can avoid this call. I want to avoid this call on every request. Instead, if the request is repetitive, I should check if that data exists in my caching, which is present on the server, so that we don't have to go outside the server to call database and increase the response time. So we will put it here. So it can be either Redis. So let's say we have Redis on the server. So what will happen is, every time the request is coming, we can check in Redis first. If it is present, then we send the response back like this. If it is not present, then only we go to the database and then put in Redis also, so that next time we have the same data and then send the response back. So again, there are a lot of different type of caching strategies, caching providers we will discuss further. So but this is overall concept of caching, to save the response time and to save the cost also, because every time you hit the database it has some cost involved. Now the next thing is API gateway. API gateway is the entry point for all the API requests. So it is mostly used in the microservices architecture, and then it can be treated as like a centralized security system. So now what will happen is, let's say instead of one program, right, you have lot of other programs, or let's say we will call it as a lot of microservices. So for example, this. So let's say you have products microservice, you have user microservice, you have orders microservice. So when I say microservice, inside it will be some algorithm or program. And now I have user here. So now the user, user wants to fetch either products or users or orders, but you don't want to give the different endpoints, because you don't want to like, you want to have that abstraction, like you want to hide unnecessary details, and also for security purpose you don't want to expose your architecture. So in that case, what we will do is we will have a API gateway here. So user will request API gateway, let's say something like, let's say slash users. And now inside API gateway, we will have a logic. If this request pattern is coming, call this microservice, right? And if, let's say, let's say another user is calling slash orders. So inside API gateway will navigate to this, and then API gateway will receive response, and response will be sent by API gateway. So in that way, we can prevent users from knowing the internal details of our system. And it is also, you can do a lot of security configuration here. You can do the rate limiting here. That is one of the important thing we do inside API gateway, rate limiting. That is like, one user can only call your API, let's say 100 times per minute. If user will try hitting more than 100 requests per minute, then it will get blocked. So this is like to prevent the bot attacks, because when your APIs is exposed, anyone can try to shut down your system by sending unnecessary requests via bot. So in every big enterprise applications, they have API gateways, they have proper rate limiting, so that no one will do the DDoS attack on you and then shut down your server because of the lot of excessive requests via bot. So same thing here. So we already discussed rate limiting, as API gateway and rate limiting are linked with each other. So rate limiting is restrict the number of requests a user can make in a time window, like 100 requests per minute, 200 requests per minute, right? So whatever the contract you have between you and users, because it will help to prevent DDoS attack, and specifically your API will be not abused, specifically if it's free or open source API. So that is how the rate limiting works, and rate limiting is usually configured at a API gateway level. So the next terms are stateful and stateless system. So they are also widely used when it comes to system design. So stateful is when you maintain any client session or data between requests. For example, like shopping carts, login sessions. And stateless is which doesn't retain any client data between requests, that is microservices or REST APIs, right? So now where the stateful and stateless system fits here. So for example, let's say I have user, and user is calling my microservice. So let's say it is sending username and password here. So when it comes to stateless, right, or microservice, what we will do is we will validate the username and password from the database. So I will just copy this database here. So we will do this here, and then if the username and password is valid, we will create some token system here. Like we will use JWT. That JWT concept we will discuss in detail also. But let's say some token. So based on the, so if username and password is correct, then some token will be sent to the user, and the next time that token can be used to call the service again, and then in the microservice we will have a logic to validate the token and give the response. So in this scenario there is no state involved, we are not storing anything on the server here. So if let's say the microservice is installed on, let's say, server here, so we are not storing anything, right? We are not storing. Next time if token is coming, our program will able to identify or decrypt the token, and will able to tell if the username or password, or if the token is valid or not, right? If token is expired, we can check from database and give the new token. So in this scenario there is no state involved. So this is known as stateless. So you call same API from any machine any number of time, it will give you same response. If I deploy my microservice, right, in maybe 500 different servers, and then also we don't have to worry that our system will fail, because it's stateless. Every request is served independently. But in the stateful system, we will not use token. Instead of using token, we will store some value in the server. So let's say based on username and password, I can store here some variable. Let's say logged is equal to true for this user ID, anything, like it depends on your architecture. But this boolean value will be at a server level. Then the scaling issues can come because we can't blindly do the horizontal scaling because we have to maintain the state also. But overall, in enterprise applications, most of the systems are designed stateless, like via REST APIs or microservices, because it is very easy to scale. So next two concepts are related to databases. So one is database sharding and another is database replication, or in general replication. So replication is meaning like creating a copies of data to ensure availability. So for example, you have some important documents you put in your laptop, plus you create a copy on OneDrive or Google Drive, just to make sure if your laptop is stolen or if your laptop died or laptop crashed, you have a available copy on the Google Drive or OneDrive, or on the cloud platform. So that is in general we call it as a replication concept. And within the application you have backup, you have failover support, you have read heavy systems. So within replication, so simply we can put it as a having a copies of important things as a backup and failover. But database sharding means splits larger database into smaller chunks for better performance. So it is like a splitting the entire database. So if I go here and if I will try to explain you visually here, so what I will do here, let's say you have a big database, right? So you have a big database. And now if we, let's say, take an example of Slack. So if you are aware of Slacks, you will have a different channels within Slack. So what Slack do is for each channel, it will have the database shard based on channel ID. So based on the channel ID, right, it will divide the databases. So let's say when user request for that channel, so based on the channel ID, the request will go to either this server database or either this database or either this database. So this concept is called as sharding, where we divide the bigger databases into smaller databases based on some key, so that we can improve the performance and avoid a lot of load on single database. So this is known as database sharding. And there is also one concept which is known as database partitioning. So in database partitioning, you don't create the clusters of database. You will always have one node or one database server, but within the database server you will do the partitioning of data at a table level. So let's say before you have some table of, let's say, 1 million rows, and then with the help of database partitioning you will divide that table into, let's say, three tables. So first, let's say 300 records, 300k rows will go here, and then 300k rows will go in the second table, and then maybe 400k will go to the third one, something like this. So one table is getting divided into multiple tables, which is call it as a database partitioning. But difference between database partitioning and sharding is, in database partitioning still you are playing inside one node or cluster, but in database sharding you are dividing your database into multiple nodes based on some shard or key. So let's talk about event driven architecture and message queues. So these are related to each other and these are very common terms used in system design. So event driven architecture is when you trigger some reactions or logic based on the events. So event can be anything. It can be like, let's say some order is placed on your website. You can treat it as an event. Or when someone give you the feedback on your website, it can be triggered as event, right? Any action can be treated as event based on your use case, and based on the events you send some messages or events to different consumers. So for example, notification service, right? So when you go to YouTube, you do turn on notification, for example, right? And then when that creator will add a video, you will be notified that the creator have uploaded a new video. So uploading a video is kind of event to the YouTube, and you have subscribed to that event. And similarly, millions of other people would also have subscribed, right? So that means in case of that creator, when upload a video, it is an event, and it is getting notified to whoever people or whoever consumers have subscribed for that event. And to achieve that, we use message queues, like we have Kafka, we have RabbitMQ, right? There are a lot of message queues available, so we can decide what message queue to use based on our use case. So if I have to explain it visually, so let's say if any user is going to your website and placing the order, so now order placed, we will treat it as an event. So let's say this is one kind of event. So now once the order is placed, you want to send this event in a, let's say, message queue. So let's say this is kind of message queue, right? So what we will do is, so order placed, and it will all happen in asynchronous. You don't want to, wait user until everything is done. So this whole thing will happen asynchronously, and once the order is placed, you just trigger event and just send the response back that your order have been received, right? Something like that. So now you will send an event to the message queue, something like this, right? And this event will contain all the information about order ID, what kind of order, number of items, price, everything, right? So it will be in the JSON format. So you send here JSON, and then based on the message queue, the different consumers will subscribe to this message queue. So let's say I have three consumers. So this is just to give you a rough idea, so we will discuss in depth when we proceed in this course. Let's say this is consumer related to inventory. So now once producer send this event to message queue and this user have subscribed to this event, right? It will go here and it will do the logic based on the event. Let's say I ordered mobile, and then the logic of this consumer is to reduce the inventory, whatever is order is placed. Similarly, we will have another consumer based on, let's say, shipping logic. We will have another consumer for analytics purpose, right? So this is like how it is done. So based on the different consumers, as all the consumers are handling different use cases, so based on one event you can have thousands of consumers also, and all the consumers will get notified when the producer will send the message to this message queue. And if we talk about Kafka, so this message will go to the topic. So this can be basically a topic in Kafka, and all the consumers can subscribe to this topic so that they keep listening. So this will be a producer, this will be consumer listener, right? Which will always listen to this topic, and whenever any new event comes to this topic, the logic of this consumer will get triggered. So this is how all event driven programming works, and whatever this logic is here, it will always work asynchronously, because we don't want user to wait until everything is done. Yeah, in some cases it can be synchronous, like in case of banking, in case when you do payment from your ATM card. So you want everything to be synchronous because there they want consistency more, and that is the use case where they will do synchronous. But in most of the use cases, these kind of logics which are running in the background can be achieved asynchronously with the help of event driven programming and with the help of message queues like Kafka. So now our next is fault tolerance. So fault tolerance means system continues functioning even some components fail, right? High availability system. So like in our home, when we all will have some kind of inverters or generators. Like if there is a power outage, the inverter will serve us the basic electricity, right? Something like that. So how well your system is designed for fault tolerance. So if I go here and if I go to the previous example here, so in this case, right, so we have two servers. So let's say one of the server goes down. So now this server is not working. Just an example. So when this server is not working, is your system sufficient enough to handle all the requests even one server is not working, let's say for 5 minutes, and then after 5 minutes it will restart and go up. So during that window, your another server should able to take all the requests, or it should be having self-healing mechanisms. So when you use Kubernetes, right, you have different pods. So if one pod goes down, the another pod will automatically start. So it all have self-healing mechanism these days in Kubernetes. So this is how it is. And even let's say you have two databases and then one database is not working, and if your Redis is not working, so you all have to do the testing by shutting down all the components one by one, and that is also known as chaos testing. So Netflix and other big enterprise companies really do chaos testing on E3 so that they can test like their system is fault tolerant and prepared for disaster recovery. So imagine like this server is in India, and then something happens in that part. Let's say it is in some city ABC, and that city got hit by fire accident in the server room. So this server is physically now gone, right? Because there is a fire incident. So these kind of disaster recovery exercises also they do, and which is known as DR exercise. So DR exercise, chaos testing is all part of fault tolerance, because you are testing how your system will behave when any component goes down, and it will also test your code logic, right? Because in code logic, if you're working in Spring Boot or any other microservices, you might have circuit breaker pattern, you might have retry, right? So all that thing also comes under fault tolerance when it is at a coding level. But at a system design level, you will do chaos testing in production, you will do fault tolerance and disaster recovery exercise. So you should be aware about these basic terms which are being used in system design. So data partitioning we already covered when we discussed about sharding and replication. So now the next is cap theorem, right? So cap theorem is very important when it comes to do trade-offs, because when you're designing any distributed system, it all depends on your use case, what you want to trade off, right? Because every system have a different requirement. So basically if I draw here, right, cap theorem, so what it looks like, so you have consistency, and then you have availability. So I will put like this, availability, and then I will put as a partitioning tolerance, partitioning maybe. So I will just put it like something like this, it will look okay. So let's say this is consistency, right? So I will just write it here. So let's say it is consistency, right? And then this is availability, and this is partitioning. So I will just write it like this. So now if you see here, according to CAP theorem, what they say is not all the systems or databases can achieve all these three. So consistency means like every read will get a latest data. Every read will get latest data. And then availability say like every read will get data, but it can but it might not be latest, because we are using eventual consistency here. So partitioning mean like there will be multiple nodes, so that if one node is failed, right, the system will still keep on working. So here this portion, right, so if you see here, this portion is CA, this portion is CP, and this portion is AP. And according to cap theorem, this can't be achieved where we have all the three. So we can't achieve all the three parameters. So we have to decide based on our use case whether you want to trade off your availability, right, or whether you want to trade off partitioning, whether you want to trade off consistency. So either you can have CA, either you can have CP, or either you can have AP, right? So all the databases have different use cases. So some prefer CA, some prefer CP, and some prefers AP, right? So if I talk about MongoDB, right? So MongoDB always prefers CP. So MongoDB will fit here. So MongoDB will prefer CP. And if I talk about AP, so AP will be like with Couchbase or Cassandra. So AP will be here, Couchbase or Cassandra, because they prefer availability and partitioning over consistency, and MongoDB prefers consistency and partitioning, and so it prioritizes data correctness basically. And if I talk about CA, consistency and availability, it is like you have SQL or PostgreSQL, where there is no partition, but which is very rare in distributed systems. So these days everything will have partition, but it will fit something here. So according to your use case, let's say if you are having banking use case, so you definitely need consistency, right? You can't show incorrect balance to user even for some millisecond. So that's when you will choose MongoDB, because you need consistency and partitioning. Availability is okay because you can show like to user the application or service is not available now, please retry later. So in that case, consistency and partitioning makes sense rather to show some incorrect data. But in case of another use cases like let's say e-commerce, social media, I will go with availability and partitioning. Like even you don't see the latest post immediately. Let's say I posted, and if you are not able to see my post in next 5 seconds, it doesn't make any difference, right? Because eventually you will able to see that. So this is high level of gap theorem. And then we have load testing. So load testing is how the system performs under stress, right? So this is like you can use JMeter. If you are having some microservice, you want to know like your microservice, how it will behave under lot of load, right? So based on load testing only, we are able to get our throughput. So that's how we calculate. So let's say I created a API, I put it under load, let's say 100 users per second, and I will check the performance metrics. Then I will go for 500 users per second, right? So whatever number I will get from performance or load testing, then I will able to calculate my throughput. Okay, my service will give you throughput of let's say 1000 transactions per second or 1000 requests per second. So that is known as load testing. Then we have distributed system. So distributed system, like in enterprise applications, we have systems which are event driven and microservices are there. So everything is distributed, right? Scalable. So like all the microservices will have their own servers, own databases. It's not like everything is working on single server and single database. It might have thousands of microservices, thousands of different pods, thousands of different databases. So everything is working as a distributed system, right? And then we have indexing. So indexing means like creating a shortcuts for faster data retrieval. So we all know, like if you have worked on basic databases, you create a primary index, right, for fetching the data faster. So that is known as indexing. Then we have logging and monitoring. So whenever you create any application or service, the logging is very important, right? Because you want to track the metrics, you want to debug, or you want to have a reliable system, you want to send analytical reports, you want to analyze what user is doing and how my code is behaving, right? So all that things are under logging and monitoring, and you might have to create a different dashboards for different users, stakeholders. So it is like a CCTV cameras for your software, so you can see exactly what happened at what time. So you should be able to log properly in the code, so that whenever you need anything, you should search by timestamp, and you should have all the logging metrics that you need to debug the issue, right? Because if there is no log, no software engineer can do anything, right? With logging only, they will able to check the errors and improve and solve errors. Then we have strong and eventual consistency. So that we already talked in gap theorem also, right? Eventual consistency. So strong consistency mean all users should always see the same data, like banking. So it can be always synchronized. But eventual consistency means data may be temporarily inconsistent, but eventually becomes consistent. It is like when you're using Google Docs, it might sync after let's say half second, right? Still the gap is time gap is very less, but still it is using eventual consistency. And then we have availability. Availability means like how good is your system when it comes to uptime. So these days all the availabilities are like 99%, 99.9%, right? So we will discuss about availability in detail in coming chapters. But availability means like out of 365 days, how many days your system is up, right? So in that way you can calculate the availability score of your application. If your application is up whole year, it will have 100% availability. If it is down for let's say 2-3 hours per year, then it might be 99.99, right? Something like that. So availability is very important, especially in critical applications like banking, e-commerce, social media. And then observability. So observability is linked with logging and monitoring only. So it is like to monitor internal systems using logs, metrics, and traces, right? So it is like a dashboard kind of thing. So if you have seen your car dashboard, it show fuel, speed, engine light. So same way, like you will have the dashboard where your business CEO can go, okay, these many services are running, right? Because if you talk about leaders, they will not go into Splunk and check the logs, right? They will might go to Grafana dashboard and they can see the view of entire ecosystem, like of the distributed system. So if they have 500 microservice, so they will just go to dashboard and see what's the status of these 500 services. Are all the services up? What is the performance? What is the error ratio? What is the availability, right? So all that things can be seen under one dashboard, and that is very important when it comes to enterprise application, because you can see a bigger picture under one dashboard. So these are all the concepts, like very common terms. So hopefully this video was helpful. Hi guys, so this video is all about scaling your application up to million users. So let's say in the legacy application, right? So you have one web application and you have deployed the code in the server, right? And the user will request your application, and your application will send the request to the server, and then the server might go to the database and give the response back to the user, right? So this is how generally it looks, right, at high level. So it's very basic, but if your application is a small scale application, right, so this design is more than enough, right? So there is nothing wrong in this design, right? So it will work well if you have a less data, if your traffic is less, right? There is nothing wrong. But now the issue starts when the traffic is too much, right? So let's say your lot of users are hitting your application at the same time, right? So then you have to do something at the server level, at the database level, at the architecture of the application level, right? So you have to do all that things. So now let's say we want to scale this application, right? So traffic started coming to your application, now you want to scale, right? So the first step as a developer will be to do the vertical scaling, right? So what I mean by vertical scaling is, so you need to do vertical scaling. Vertical scaling means, like if your server was, let's say, 16 GB RAM, right? Now you want to increase to 32 GB, now you want to increase to 65 GB, right? That means you are not increasing the number of machines, but you are increasing the configuration of your server. So it will look little bit like this, right? So you increase the server size, now user will send the request, now your server is able to handle more requests because you increased the RAM and configuration of your server, right? Traffic is now doubled, right? So now in vertical scaling there is some limit, right? How much RAM you will keep adding, right? It's also not optimal to keep only one server, right? What if this server failed, or if server have some disaster, right? And if server got some issues, right, then your whole application will be down. So the next step comes is to do horizontal scaling. So now I will do vertical scaling plus horizontal scaling. So something like this, right? So what I will do, instead of one big server, I will maybe have four small servers, or I will have four big servers, or maybe I will keep adding based on the traffic, right? So now I have multiple servers here, right? When the user will call our application, right, there have to something in between, right? So we call it as a load balancer layer, right? So what I will do, I will have here load balancer, right? And what is the purpose of load balancer is to send the request to any one of the server based on different algorithms. So there are different algorithms of load balancer available. Based on the load balancer algorithm, either request will go here, either it will go to any one of the server, right? Here, or this server, or this server, right? And then we have database. This is how it will look. So now our system design is getting improved, right? So basically now we have added more than one server, and now we have added load balancer, and load balancer will work on some algorithms. So we will not discuss about algorithms in detail, but at high level, right, we have, first thing is round robin, right? So first request goes to first server, then second, then third, then fourth, then fifth request goes here, sixth here, seventh here, eighth here, right? So one of the algorithm which is simpler one, which is round robin, right? And the second one which is commonly used is least connection. So that means, let's say this server have 10 active connection, this have 100, this have 5, right, and this have 50. So the with the least connection is this server, right? So load balancer will see which server have the least active connection and will send the request to that server, right? And also these both can be combined with the weighted weight also, server weight. So what does this weight means? The configuration of your server. So in this case all the servers are equal, so it's okay, right? But sometimes let's say one server will be double the size of this server, right? So what does that mean is this server should able to handle double request in this server. So that also is one of the way of doing it. And the other one is IP hash. So IP hash is mostly used for online gaming because they don't want to spoil your user experience, right? So what will happen? This user is coming from some IP, right? So load balancer send the user one request to server one, right? So next time when user one comes from same IP, the request will go to the same server. So you would have seen the gaming thing, right? When it got disconnected, it immediately get connected, right? So that's why the IP hash comes. So again, we will not go too deep into this, but these are the high level knowledge you should have about load balancer algorithm, right? So now what is the next step, right? So the next step is to do the same as at database level, right? Because now the traffic is more, right? Now the traffic is more requests are going to database, right? So same thing we will do for the database also. Instead of application directly calling the database, right? So again we need something in between, right? Again we need a load balancer for the application and database layer, right? So here also we can add load balancer, right? And then here we will add the database layer, so which will look something like this, right? So load balancer, and then load balancer will send request to any of the database. Again it also can have the algorithms also, same the way we discussed above. So now if you see something, the design will look like this. And also database, when you do horizontal scaling, right, you different things comes into picture, like database sharding concept, right, is there, and replication come into picture, right? So again we will not go deep into this sharding and replication, but here if you see, let's say we have three databases, right? So one can be a leader database and other can be followers, or we also call as master or slave, right? So whatever write operation will happen, it will happen on master or leader, and then the data replication happens between them, something like this. So it will look like this, all the write operation go here and then it get replicated, and again replication can be asynchronous also and synchronous also. So I will make separate video on sharding and replication. Now if you see, now we have more than one server at the application level, more than one server at a database level, and then we have load balancer in between, right? So now the next step to improve this design is, like, instead of every time doing the database call, we can use the caching mechanism, right? So if I go here, right, and I will just reduce the size little bit. So what I will do here is, so instead of this application making directly call to database, right, load balancer, first I will check here, right, cache, right? It can be like a Redis. So I will check if this data which I am looking for, right, is present in cache or Redis or not, right? If it's present, then the response will go from here. If not present, then we call the database load balancer, and then the load balancer will give the response to the server, right? So mostly it will look like this, or I will just say data present, right? Then give the response back, then data not present. So this is looking good. So now here one challenge is there, how you will maintain the cache with the database, right? So let's say some write operation happened right here. Now you have to put that record in the cache also, right? So basically the database and cache should always be in sync, right? So for that we can use Kafka Redis connectors. Okay, so again we will not go deep into this concept, but with the help of this, right, Kafka, like event driven messaging, they have some connectors. Whenever any update will happen in the database, right, the connector will update the data in the cache, and once it is updated in cache, the updated data will be serviced out to consumers, right? So this is the extra step we have to do when we introduce caching in our mechanism to sync the data between database, right, and cache system. So this is now how it looks, right, with caching. Now if we go next level deep, right, what we can do, we can introduce CDN here, right? So CDN will be for the static files, right? When you call the web application, there are a lot of HTML, CSS, JavaScript files, right, which can be fetched from CDN instead of directly going to the server, and then we can fetch the data from cache, and then we can give the response to the user. So this is how it looks right now. So now let's say we divide our application architecture to microservices, right? So for each microservice right here, we should have the similar architecture. So it will look like this. So let's say CDN is at the web application level. I will remove that. But let's say now this whole architecture is for each microservice. So let's say this is your first microservice, which you call it as a, let's say, get users, right? And then in a similar way you will have other microservice, right? You can call it as get accounts, right? Or get products. Each of the microservice should have its own architecture like this. So if you have 100 of microservices, right, the architecture looks like this. Every microservice is loosely coupled from each other, and it have its own servers, have its own infrastructure, have its own caching, have its own database. Everything should be loosely coupled, right? So imagine if you have hundreds, thousands of microservices, how big your system is, right? So I will just remove this. This is just for the explanation. And also for the intercommunication, right? So sometimes microservices have to communicate with each other, right? So if they are doing it synchronously, right, so they can use, like in Spring Boot we use like Eureka, right? We use Eureka, Netflix, Discovery, right? Service Discovery. But if it's asynchronous, right? So, for example, we don't need the data or anything on the fly. I want to send some logs to my logging service, right? So, let's say I have one logging service here, right? Which all the microservices will send the data, right? And this logging service, let's say, is connected to some dashboards, right? So it can be, let's say, Grafana, right? So we are using Grafana and Prometheus. So all the services can send the events, right, to this logging services, which will be asynchronous. And based on this, you can view the metrics on Grafana or manage incidents, right? ServiceNow is there. So all that stuff you can do, right, based on this. And then these asynchronous thing again we can do via Kafka, right? So we will again not go deep into Kafka, but this service will have like Kafka consumer, right? So which will keep listening on some Kafka topic, and then Kafka producers will send the events to the Kafka consumer, and then we will have all the logic here. And once we do the logic here, it will do like uh, reporting management, incident management, email trigger, all that things we can handle here. So this is how it will look, right? And we use Kafka for event driven architecture. And now the last thing is like to we need to take care of the disaster also, right? So that's why when we deploy anything on the servers, right, maybe we need more than one region. So if I will copy this, right, so for each microservice they might have different regions, because let's say this region is for get users, let's say US region, right? And inside US also they can have different. Just for this example, just to show you the concept of disaster recovery, right? And also they have different regions based on the market level. So let's say it is India region, right? And now let's say this is required because let's say in US region, if there is some earthquake, fire, any natural disaster, then this architecture will go down, but still this region will be up, right? So this is one of the benefit. Other benefit is this is a India user, right? So India user request will go to India region because it will be faster, right? And the US region request will go to US region, right? So that's why big companies have lot of data centers. High level, we have three different API patterns. First one is REST, second one is GraphQL, and third one is gRPC. Let's discuss it one by one. So REST simply means representational state transfer, and REST is basically not a framework or a library, it's an architectural style, and it uses URLs and HTTP methods, and it supports multiple data formats like JSON and XML, but JSON is being used widely these days. If you see this example, right, so consumer will call your server, and the request HTTP method, right, will be mentioned here. It can be either get, it can be post, it can be put, it can be delete, or it can be patch. So we have 5 type of HTTP methods. So get is for fetching resource, post is for creating a new resource, put is for updating resource, delete is for deleting resource, and patch is for partially updating an existing resource. And whenever server get request based on the HTTP method, it will process the request, and then the response message will be sent with HTTP response status code. It can be 200 for success, it can be 500 for internal server error. So high level we have 5 different categories of HTTP response codes. So first one, which starts with 1, they are informational response. Second one is starts with 2, which is successful response. Then 3xs is for redirection, 4xs is for client error, like 404 not found, 400 bad request. 5xs is related to server error. It is prone to underfetching and overfetching. And this problem was resolved by GraphQL, which is another API pattern by Facebook in 2015. GraphQL said, describe your data, ask for what you want, get predictable result. So here is the example of the GraphQL query. In this, I am saying I want name and height of the hero. And in the response, you will get exactly same response. You will not get any other property of hero. Fetch multiple resources. So let's say you have get products, you have get address. Call 2 different REST APIs. Either in your code, maybe you can create another REST API combining 2 of them, but how many times you will do that? You have to keep combining based on each consumer requirement. And with the help of GraphQL query, you can fetch both product and address from the server, and also you can mention what fields you want. There are multiple queries to handle, so which makes caching implementation very difficult in GraphQL. So the third one is RPC. RPC stands for remote procedural call. gRPC is basically a framework by Google, which was launched in 2016, and it is mainly used for server to server communication. At high level, the client application can directly call methods on the server application as if it was a local object. Client and server communicates via HTTP2 using a binary format, so to which it's very efficient, and that's why it's very fast. But binary format is not as readable as JSON format. Let's say you have consumers, and your consumers can be web app, mobile app, any other app, and you can enable GraphQL for your consumers, because let's say web app is using GraphQL to fetch 50 fields, whereas mobile app is only using 10 fields, so it will only pass 10 fields in GraphQL period. Other app might be using all 150 fields. And the GraphQL request can go to API gateway, and API gateway can internally communicate with services like get products, get offers via gRPC. It's an internal service, that's why gRPC is very efficient for internal API communication. And for external services, you have to send data to external services like e-commerce, CMS, or logging system, right? In that case, you can use REST. So if you see in this architecture, we used GraphQL for our consumers to provide them flexibility for queries generation so that it will not lead to underfetching or overfetching. Internally, we used gRPC with API gateway and internal service communication. External services, REST is still ideal and is widely used. So if we compare the differences, first one is REST, GraphQL, and gRPC. So REST can support JSON, XML, and extra, but JSON is widely used. GraphQL uses JSON format, query language required. gRPC uses protocol buffers, binary format. Data fetch, extra data might be returned. Here in GraphQL, allow clients to select specific data to fetch. But in gRPC, no advanced client query, extra data might be returned. So REST and GraphQL are supported by all the modern browsers, but gRPC have limited support. It might need some extensions. Code generation, it can be generated via Swagger or OpenAPI. GraphQL, almost they need some additional libraries, but they are readily available. But in gRPC, mandatory code generation with protocol buffer compiler. Response time slower compared to gRPC because of text fix format, because we have JSON and all other things. But gRPC is faster due to binary format and HTTP2. Caching is very mature and straightforward in REST, but in GraphQL it can be difficult because there are a lot of queries, post methods, and all. But gRPC, it is not supported by default. Intended usage, specific for public facing API, we should use REST, but GraphQL is suitable for APIs needing flexible queries, and if you have a lot of consumers which have different requirements based on the data. gRPC definitely ideal for internal APIs and microservices communication. Hi guys, so today we'll talk about how big companies do their deployments to achieve zero downtime and high availability. So let's talk about blue-green deployment first. So let's say your consumer is hitting your API. Once your API is hit, it will go to load balancer, and then after that, load balancer will send that request to production region, right? So this is the usual flow which happen for almost every project. So in case of blue-green deployment strategy, we will have one identical production region. So the live region, which will be called by our consumers, will be the blue region, okay? And the identical region, we will call it as green region, okay? So this is how it will look. So in production, we will have two identical regions. Let's say as a developer, you are doing some code changes and now you want to push that feature to production. So what you will do, you will just push your code changes in GitHub, and after that your CI/CD pipeline will run. So inside this pipeline you can run automated test cases, you can deploy on your QA server, you can do regression testing, performance testing. So it depends on your application. And after that it will do deployment on the green region, so it will not do directly deployment on blue region. So this green region, once the code is deployed, again, to be 100% sure, the developer or the business owners can hit the green URL. So the green URL is not publicly available to consumers, because consumer will call, let's say, api.youtube.com. So this is our live URL which will always go to the blue region, but for green region the URL might be different, which is only known to the developers and the project owners of the application. Okay, so developers can do testing, like not the testing which will modify the database, right? Like you can do testing, like to see if the this API is giving the expected response here, right? For example, let's say you have added one field in the API or changed some logic in the API, then the developer can hit the API in the green region and see if the changes are looking as expected, right? Because both of the regions are connected with the same production database, so the database is same. So this is how it looks. And once you have done your testing on green region, just to make sure like the changes are already deployed, so once your testing is completed, you can give command to the load balancer and you can ask load balancer that you can revert the traffic to green region now instead of blue. So this region will be now your blue region because all the traffic is here, and this region will become your green region. So basically it's like a switch. So green will become blue, blue will become green, and here we have old code, right? And this will be now the new code. So now if let's say some issue is coming in the production, right, this with the new code, then it's very easy to revert back to the old code because it's already here in our green region, right? So load balancer can again revert the traffic to the old code. So that's why the rollback is very easy in this case. And zero downtime, how it is achieved, let's say when the green and blue switch is happening, right? So the load balancer will not cancel any request. So whoever consumers have established the connection with this region will get their response, and the new connections will start getting established with the blue region, which is having the new code. So that's why no request will fail, and that's why it is known as like zero downtime or high availability. So during the switch also no request is getting failed. So this is like the blue green strategy, right? But we can also do the canary deployment like with blue green. So instead of switching all the traffic here, right, to the new region, we can put some automation scripts in the load balancer and we can switch like 20% of the traffic or 30% of the traffic just to do the A/B testing kind of thing. So in case your API is not that critical, right, then the company will not spend money on two identical region, right, because the cost is getting double here. So let's say in canary what will happen, the load balancer will send the request here, and then once we want to do our deployment, we will start a new node, right? So we will start a new node here and then push our code in this node or server, and then we will ask load balancer like send 20% traffic on this new node, and once it is tested, then you can switch to your production region. So basically it will help, like this node is getting created on fly, so you don't have to manage extra expenses, and it is not like same configuration as production region. It's just a one node or one small pod or server, right? But in blue green, if your production region is having 10 servers, your green region will also have the same number of servers. Hi guys, so today we will talk about trunk-based development, which is being used in most of the companies nowadays. So all the companies want their development process should be smooth so that their deployment can happen as frequent as possible so that their time to market is less. So to do all that things, the software development process should be streamlined, your test cases should be automated, so your deployment process should be smooth. So we will look into how the trunk based development process works to accomplish all that things. So let's say we have one Scrum team here. So Scrum team is basically used in Agile. So basically in Agile, whole software is built incrementally. So they will pick some part of the feature of that software and they will develop that feature and they will put that feature into production. So this is all about Agile. So we will not go that deep into Agile in this video. I will create another video only for Agile. So in trunk based development, you have one main branch in GitHub. You also call it as trunk. So the purpose of this branch is this branch should always be deployable. So meaning like this branch should be latest and all the deployments should happen from this branch. Okay. So let's say the product owner assign two features to the team. Okay. So let's say two features are assigned to the team. And now that two features, let's say, are picked up by two developers. So what they will do, what will be the first step? They will go to main branch and they will create the new branch, feature one, let's say. Okay. So again, the second developer who is working on feature 2, he will also do the same thing. He will go to the main branch and will create his own branch, let's say feature 2. Okay. Now the two branches are created from the feature branch, feature 1 and feature 2. And now the developers will work on these branches to complete the work in these features. Okay. So let's say the feature 2 branch is completed now. The work is completed. So the next step will be, so the developer will create the pull request to merge that code into the main branch. So once this pull request is created, then your continuous integration come into picture, right? So in as part of continuous integration, your project should have automated test cases. Like it can be unit test cases, it can be regression, it can be business test cases. So it totally depends on your project, but as soon as the pull request is created, this should get triggered. So we can use GitHub Actions to trigger automated test cases when the pull request is created. So your code review process should be also fast, so that once let's say I'm creating the pull request, so the first step will be all the test cases are running against my code. And once all test cases are passed, so this process is passed, so inside that the code review process should also be there, so that the other developers of the team should able to review and give their approvals on it, right? So that's how it should work. Once everything is done in this step plus code review, the code will get merged into main branch. Once the code is merged to the main branch, the deployment process should be triggered. Again, we can use GitHub Actions for this, or you can use any other tool also. So deployment process will trigger like this. So let me arrange this. So again, whole idea of trunk based development is that main branch should always be deployable and latest. So once the code is merged, our deployment process is triggered. And let's say most of the companies will have like QA environment, and some will have a development environment also. So here, let's say if we have QA environment and then we have, let's say, production environment here. So once the deployment is done on QA, then again, before moving to production, in this step, you can also do your testing again. Okay. So, and in some of the cases you might need, like, okay, the code is deployed to QA and maybe someone from the client side have to give you approval on QA, and then you can move your code to production. But QA to production also should not take much time. It should be as quick as possible based on your project or application. And between QA and production, again, you can do testing, like maybe performance testing or regression testing. You can do that in this step on QA server, and once it is okay, then your code will go to production. Also, one case can be the production server is always connected with your feature database. Okay, feature flag database. So that is really important. But again, it depends on your application. So what that means is, let's say the feature 2 was already merged in main branch and it's already deployed, but this feature will go live after 1 week, let's say. So this production, so the value of feature 2 flag will be false, okay, in this database, so that your code can read from this database and will able to get the value if in production feature 2 should be visible to end consumers or not. So this step is really important. And also in production environment, you might have different deployment strategies. It depends on your project. So if let's say the team is using blue green deployment, so they will have two regions like blue and green, similar regions, and the blue one will be active. In that case, the deployment will first happen to green region so that they can do their validations. Everything is working fine. All the validations can happen in green environment, and if it's all stable, then the green can be switched to blue environment, so that in case you have any issue in blue or live environment, you can immediately switch your code here with the last release. But again, the point is it's like not that simple, like you just move the code from QA to production. So this part is really like where all the deployment strategies comes into picture, so that there is no impact to the end consumer. So if you found this video helpful, don't forget to like, subscribe, and hit that bell icon for more programming content.